So, welcome to the seminar offered from the IAPS Institute here in Rome. Today we have the honor to host Andrea Socci from University of Vienna, where he's working with Professor Alvaro Acar in the field of star formation. Andrea is a young student. He's completing his PhD. He's ending his PhD now, but he already worked in the field of high mass star formation with Francesco Fontani and Leonardo Testi during his master thesis, and then he moved to University of Vienna to continue his study in star formation, shifting from the high mass stars to the more large problem involving either the entire clouds of the filamentary clouds that are where the high mass star formation is happening. Is recently published a very interesting paper based on ALMA data. He's also an expert of ALMA data, using and analyzing. So we decided to invite him to give us a snapshot of what are the latest results on the observation of the nearest high mass star forming cloud, that is Orion, that is a prototype generally used in this field. So the floor is yours, and you have 40 minutes for your talk, and then we will have you questions.
Okay, thank you so much for the introduction, and thank you all for coming. I mean, I would say that I'm an expert on ALMA data, but we will try to see who is exactly at some point. Yes, who is. But thank you for having me. And today I will be presenting this work, fiber networks in Orion, star formation and width variation that I've been done with the eMERGE team in Vienna, and that is the, let's say, summa of two recent papers that I've published. I will follow this outline. I'll follow this outline for the talk. So I'll give a bit of context of filaments and fibers in the interstellar medium. Apologies if this is a repetition for many of you, but I thought it would be a good starting point to trigger why we decided to go with this eMERGE ALMA survey, and a bit about the observations and the analysis and the main results coming from this work, both related directly to the fiber networks, in particular about the fiber density and mass relation and the mass length relation found for these fiber networks, and then on to more about the radial profiles of these fibers and the environmental dependence that they may have based on density and pressure. And then I will wrap up with a summary of this talk. So for the context, I will start very far away, let's say, but don't worry, I will move forward very fast. So I will start here, 1907, with this beautiful photographic plate of the Taurus molecular cloud, where we see these, for the first time, these dark lanes connecting nebulae where star formation was happening. And already Barnard highlighted how these dark lanes connecting these star formation sites might have been relevant for the star formation process. And then starting from this point and for a century afterwards, we have been studying filaments in the interstellar medium across the galaxy. And at some point, we came to Herschel, which was able to discover all these filamentary structures in the galaxy, across the galaxy, and in the interstellar medium. And as you can see here, the same exact filament, Linz 1495, now seen not in extinction, but in dust thermal emission. And as you can see, the main structure is the same, but you see that there is much more complexity to be seen thanks to these observations. And for the sake of this talk, I will focus mostly on the filaments in the solar neighborhood, which are part of the Herschel Goldbelt survey, which include some of the closest star formation sites like Taurus, Polaris, IC 5146, and the Aquila molecular clouds. And as you can see in all of them, the filaments are found to be ubiquitous or to be permeating clouds. And but from these observations, a lot of properties have been derived for these filaments. Some of them controversial and has sparked a lot of discussion in the past decade. So in general, these filaments are very large structures. They are, in most cases, above 1 parsec in length, up to tens of parsecs. And in many cases, they are also massive structures like this one that I show here in torus. And massive in the means of line mass, which is the mass per unit length of the structure. And in this sense, the parameter that is usually used to compare is the critical line mass, which is instead the line mass that would be required to have at least a stability for this structure, and is based on the thermal pressure that the structure has inside compared to the gravity that is suffering from its mass. And in many cases, we found these filaments to be supercritical, which means that they would not have survived radial collapse before forming stars, which was a first challenge to explain in the field about these parsec scale filaments. Among other properties, and maybe even more controversial in the field, comes the analysis of the radial profiles, and in particular the width that was found for these structures. So from the analysis of some radial profiles like the one that you see here, the fit would provide information on the peak column density and the width, so the radial extent of these structures. And it was found that despite these clouds being at different distances and possessing different physical properties, the width of the filaments harbored inside would be mostly around 0.1 parsec, which was a surprise and also a challenge to explain in many cases. Even maybe more surprisingly, directly connected to this one, is that the width was constant, not only across clouds, but also in function of the peak column density derived for these radial profiles, while instead, both from the theory of filaments and from simulations and models, it would be expected that the full width of maximum, the width of these filaments would decrease with the peak column density, which instead is something elusive, or at least has been elusive for a long time. So as I said, these three things were a challenge to explain, and many works, of which I only show two here for the sake of time, many works have been trying to explain this through modeling, and we see here two type of models based on confined filaments, either from an external pressure, either being a thermal pressure, so just the thermal gas that confines the filament, or from accretion motions towards the structure. And we see that while the models can reproduce the observations from the Herschel Observatory, still at some level, it is expected that above a certain threshold, the full width of maximum should decrease with the peak column density derived in these filaments. Then came the fibers as another filament family, if you may say so, of which from molecular lines observations was found that these monolithic structures seen at parsec scales would instead be composed by several, hence in this case, of velocity coherent objects, meaning structures that are both continuous in space and in the velocity axis, which is probed by the molecular spectral lines. And now if we, let's say, introduce or recalculate the same parameters for the fibers, we see that these objects show in general line masses that are lower compared to monolithic parsec scale structures, and their corresponding stability condition, which is defined as virial line mass, because now it also has not only the thermal, but also the non-thermal motion assumed as support against the effect of gravity. We see that these two parameters are much closer in value, which would explain why we see star formation happening within these filaments, is because at some point there is some further fragmentation into smaller structure that then would harbor the cores and possibly the protostars. As we move from single dish to interferometric observations, we see that fibers are found at different scales, but they mostly retain the same main properties that are In general, they appear to be subparsec structures and also show in general subvirial a subvirial condition and subsonic to transonic motions. So their turbulence should be already dissipated at scales of subparsec sizes. Here I show one example of fibers found that is a selected example because the supervisor said to me to put this one up. But because the two regions are also presented later, and we see here how these fibers permeate these two regions, which are OMC1 and OMC2 in Orion, and they follow nicely the column density material probed by SCUBA. But from the image, we can also see that these are subparsec structures, both in length, but also in width. And in fact, not only here, but in many other studies, especially using interferometric observations, we see that these structures show widths of 0.05 parsecs, lower, sometimes higher, but in general, different from the typical 0.1 parsec that was expected from initial observations. And at this point, we have all the questions to actually go and do a survey. And this is the Emerge-Eliarma survey, which comprises 7 subforming regions in Orion, all homogeneously surveyed with ALMA 12-meter array plus iron 30-meter single dish to recover the total flux in N2H plus 120 in the N2H plus 120 spectral line at 4.5 arc-second resolution. So we see here these different morphology for the N2H plus 120 line as we move from Orion A with the OMC 1, 2, 3, 4 regions and LDN 1641 and Orion B with NGC 2023 and Flame Nebula. And we see that the emission is always extended, but it shows a lot of different morphologies. And what we want to do with these data was to actually explore the dense gas content inside these regions, having those, having them all different properties, star formation histories, belonging to those categories that are high mass star forming regions like OMC1, Flame Nebula, intermediates like OMC2, OMC3, and LDN, and low mass like OMC4 and NGC 2023. So this is a good playground to explore the dense gas content, but first of all, we need to actually connect the integrated intensity of N2H plus 120 with the dense gas. So I'll go back to this beautiful image from the Vista Observatory, where we see the bright stellar emission from the coming from the cluster obscured by the material that is front of it. And just as a qualitative, very rough, because I did it by hand, comparison, we see that the N2H plus emission mostly follows these obscuring material, this dense material in front of the cluster. Now, to be more quantitative, what we did is using a calibration of the integrated line intensity of N2H plus with the total column density provided by previous Herschel observations. To do so, we corrected the integrated line intensity with the kinetic temperature inside the region for which we have single dish observations with IRAM, and then we calibrated this factor against the total column density coming from Herschel, obtaining high resolution, so 4.5 arc-second resolution total column density maps of our regions. And then with these 3 ingredients, we could perform the kinematic analysis and then the radial profile analysis of the structures that we could identify in the sample. From the kinematic analysis, which is an association in the PPV plane, so in the position velocity plane, we were able to identify 152 velocity coherent fibers, structures in general, that you can see here on top of the column density maps. And as you can see, as the morphology of the column density map is different, also different is the shape, the number, and the distribution of these fibers inside each one of these regions. But overall, what we saw is that these structures were mostly subvirial, although there are a few examples of close to virial and supervirial structures that are actually important in the context of sample, and we will see why. And they showed mostly subsonic to transonic motions, as was previously found for other objects of the same kind. They showed a broad range of masses going from 0.1 to 80 solar masses with a median of around 5, but in general, very constrained lengths. So sub-parsec lengths, in particular, going from our resolution limit, more or less, 0.02 parsecs up to 0.3 parsecs. Now, one test that we did was to explore how these fibers came to be and how is the connection to the dense gas content inside the region. And we decided to use this parameter, the surface density of fibers, which is the number of fibers over the mapped area of our observations, as a measure of the complexity of these fiber networks inside each one of these regions. And we see that all the different regions all show different, let's say, complexity or surface density of fibers, as you could already tell from the maps. But if we plot now this parameter against the total mass of dense gas in the regions, we see that there is a linear correlation within a factor of 2 between the two parameters. And we interpreted this as proof that the fibers are just as a manifestation of the dense gas organization. And as you have more or less dense gas, independently of the star formation history or like current definition of the region, like high mass, low mass, the amount of dense gas will dictate the amount of fibers that you can identify inside the region, as these objects are how the dense gas will organize itself, let's say, inside these regions. By plotting instead the masses and lengths of these objects in this diagnostic plot that was already introduced in ACAR 2023, we can see that the, let's say, the parameter space that they occupy is similar to previously identified fibers in other independent studies, which was reassuring on the nature of these objects. And also it's quite different from larger scale filaments like the Herschel-Goldberg survey filaments. But another interesting fact about this plot is that the scaling relation found for filaments in our galaxy, which is this MVIR calculated at 20 Kelvin, so the virial mass determined at 20 Kelvin, which was used previously by ACAR 2023, our fibers, or at least the fibers that we identify in Orion, seems to follow this scaling relation up to a certain point, and then they tend to cross, becoming more massive than growing in length. And even more interesting is that if we associate them, the protostars in our fields, meaning the class 0 objects, to these single structures, we see that those that are closer to the virial condition or even cross it are those that show the largest amount of protostellar content inside, meaning that these either drive or at least are mostly connected to the current star formation inside of our regions. So these fibers not only appear to describe the dense gas content in a region, but also in the end, they seem to connect directly to the star formation happening inside these regions. Now, this was mostly related to the fiber networks and the star formation inside them. And now we move more onto the radial profiles that we analyzed for these objects. And we managed to extract from the axis of these fibers 1,052 radial cuts, of which we managed to obtain a convergent fit for 991. The fit is just the Gaussian fit to the column density profile that you see there in blue, from which we could derive parameters like the peak column density and the full width of maximum as representative of the peak and the width of the profile, and also the kinetic temperature at the central position with the temperature profile derived from the maps, of course, at lower resolution because it's single dish data.
So the red there is the temperature profile across the filament.
Yes, yes, radial cuts. Yeah. Which another good thing, I will not go into detail on this, but another good thing and another reassuring fact was that the temperature profile is actually anti-correlated in most cases with the column density profile, which tells us that these objects are not some kind of artifact, some kind of, say, misunderstanding on our side, but they're actually structures, most likely because the temperature drops when the gas becomes densest. If we now consider the width distribution, we see that overall the survey shows widths that are well below the 0.1 parsec for filaments in nearby clouds, and instead it peaks around 0.05 parsecs and even below, and it clusters closer to our resolution limit, which tells us that maybe if we even go even deeper, possibly we would see another hierarchy of objects at even smaller scales. But for the limit of our observations, we find that overall the median value is 0.05 across the whole survey. But the histogram itself doesn't tell us an interesting, maybe more interesting information, which instead the cumulative distribution shows us, is that these widths are not only lower than the 0.1 parsec, but they also systematically change from region to region. And in particular, if we move from the left to the right, from OMC1 to NGC 2023, we see that there is a stratification with regions having broader and broader widths as we move from the left to the right. And since we observed these survey homogeneously in the same tracer and also the same distance, because Orion was, I mean, there is a slight difference between Orion A and Orion B, but it's very small. This systematic variation has to come from a physical differentiation across the regions, or at least it should be connected to a physical property. And we explored, of course, as first test, the peak column density, the density dependence on the fiber widths. So we plot here the peak column density against the Fugit maximum, now for the single objects for the fiber, averaging all the radial cuts of a single object into one value. And we see that there is quite some scatter still, but we can also see that going from the top left to the bottom right, there is, again, we see this stratification for regions like OMC4 at the end and NGC 2023 on the top left, moving towards the bottom right and seeing more values coming from OMC1, OMC2, and Flame Nebula, for example. And if we now take the average per region, we see that it's even more clear this intercorrelation between the full without maximum and the peak column density as we move from the top left to the bottom right. Although this correlation is clear, but for example, there are some unexpected behaviors like the one of OMC1 and Flame Nebula that, although not showing the highest peak column densities, they show the narrower widths. And this is something that we keep it like that, and then in a few slides, we'll see if there is any connection to other properties. But for now, by putting the Herschel-Goldberg survey regions, so this is, again, the average per region in the survey, we see that there are a few widths that are consistent with our broadest values, but in general, they are on average higher for a density regime that is an order of magnitude lower. And if we take the whole distribution from 10 to the 21, more or less 10 to the 23, we see that there is indeed a decreasing trend as we move higher in the peak column density. A trend that is somehow reproduced, although none of the models that I have introduced here that are the same that I previously showed to you, which are the accretion truncated and pressure truncated filaments, even though none of them fits the values, we see that they enclose quite well the overall distribution. And we see once more that for the density regime that was probed by Herschel observations, it's really hard to see the decreasing trend because most of the models have a flat peak at that level, while instead, as we move one order of magnitude higher in peak column density, our survey is able to probe this decreasing trend to some extent. And this was, I would say, the major finding and what we would expect, and finally we found with this survey. But as I said, there could be also another influence coming into the widths, because of course the column density alone seems to be the main driver, but there could be other environmental influences. And we explored the pressure by going back to the Viral theorem. We just assume that the external pressure is just thermal, and we try to explore what would be this pressure to have the fibers confined in the width that we measure. So we basically calculated the pressure using this equation for the subvirial fibers in our sample, because otherwise we would get an unphysical number there. But doing this exercise and putting all the values in there, we see that all the regions overall, all the fibers in our regions overall should be pressurized, at least comparing to the standard external pressure value, which is 2×10⁴ for the interstellar medium. And also what we see is that there is, again, a stratification across regions, for which those with narrower widths should have the higher pressure confining them. And in this sense, the OMC1 and flame nebula behavior of having narrower widths, although the density, column density alone is not necessarily the driver, could be explained by some mechanical pressure that is coming, for example, from the feedback inside the region that is narrowing or confining even more the fibers into narrower widths on average. So this was more speculative in the sense, because of course we assume that the pressure is just thermal. There are many contributions to this parameter, but we just tried to see if there was anything interesting in this sense, and more observations are needed towards this end to actually explain if there is any pressure confinement and what are the different contributions to it to produce these kind of structures. And then here is the summary. So we explored the dense gas organization in Orion using NH plus 120 with ALMA and IRAM 30-meter observations. And we identified, using the kinematic analysis in the PPV plane, 152 structures that we refer to as fibers within this emerging early ALMA survey of 7 regions across Orion. These are organizing networks of different complexity, but overall it seems that the complexity is just driven by the different mass of dense gas inside the region, and that the most massive fibers in our sample and those that are closer to the visual condition are actually directly connected to the current star formation inside their host region. And about the radial profiles, we managed to study 991 individual cuts, individual radial profiles, from which the widths we derive are a factor of 2 lower than the typical value for Redshift filaments, and they show a systematic variation from region to region that we ascribe to column density and possibly to the highly pressurized environment of Orion. And on top, you can see, you can scan the QR code. Those are the 2 papers that I'm referring to with this presentation. And stay tuned, because many are coming. And actually one, Eugenio knows one is accepted. So we'll see what is the reception. So thank you very much for your attention.
Thank you, Andrea, for a very nice talk. So thanks for the question. And I will give first to people that are in the audience, and then the people from home, from remote, please write in the chat. I will give you the possibility to ask a question too. So anyone has a question? Alessio?
Thanks, Andrea, for the very nice talk. So I was wondering about the trend that you find between the density and the fiber width, if you can go back to the plot. Okay, so I would say that if I just look at the dispersion of all the fibers and the Herschel data, it may also be flat if we want, no? So I was more wondering if you have some statistical tools that can suggest that indeed there is an anti-correlation. I don't know if some Pearson correlation coefficient, something that would, let's say, give some strong somehow value that may give you the hint that indeed there is an anti-correlation. Because if I look at the dispersion of all the fibers only, I mean, it's hard to tell which is the real anti-correlation here, if it's real, or if we need to get it as anti-correlation or not at this point. I mean, it may be also true that these guys don't anti-correlate between the full width and the density, and then we need other explanations. But I wouldn't really say that there is a clear anti-correlation. Don't you think? What's your feeling of this plot?
So there is, so it's not clear in this sense. So to me there is, but what I would say is, so it would need more observations in this sense, because so also in the if we include the inertial data, there are many regions that actually agree with some of the ones that we have in our sample. So these lower values, like around 0.06, they actually agree, and that distribution is completely flat in this sense, and it covers a significant part of the column density range that we have actually. So in this sense, I would say that based on the theoretical models, so we didn't do any Pearson coefficient statistical analysis. Maybe we should have, but based on the prediction from the theoretical models, we were confident that there is some kind of decreasing trend. I will not say anti-correlation because it's not a -1 slope, as you can see from the profiles. But at least the theoretical models would show this, let's say, milder decrease. Another thing is, as I said, not all the models, none of the models fit because the parameters change a lot. So the scatter is also due by the fact that we only probe a few properties of these fibers in the end. So it would require to go either higher up in the column density, then we can actually see where, for example, objects that are around 10 to the 24 would look like.
Yeah, that's probably the key.
Yeah, this is probably also the easiest thing to do in this sense. But yeah, for now, we use the theoretical models as the best explanation for the decreasing trend, and we didn't do any statistics.
Stefania, question? Juan, sorry, just one. Juan, we have a audio problem. I will read your question after the Stefania. So, okay.
Yeah, thanks for the seminar. I have a similar question. And I have a question similar to what Alessio asked, but for the mass length plot
Yes.
you showed before. And I've lost the red line. Is it a fit or is it a theoretical expectation?
No, is
Mass at 20K.
yes, is a fit. So because
It's a fit. It's not a fit.
No, it's not a fit to the data. No,
okay.
no, not in this sense. No, it's a scaling relation that was found for filaments, but across the galaxy. So it was found in CAR 2023, and is basically the velocity, the non-thermal velocity dispersion, how it correlates with the length across the filaments in our galaxy. From that, I calculated the virial mass using that scaling relation, which depends on the length, and the thermal component at 20 Kelvin. So because 20 Kelvin is the typical temperature calculated for our fibers, or measured for our fibers. So I use it as a representative, let's say, virial parameter, although each one of the structure has its own, say, virial value. But it was just to see if there was a trend with this scaling relation.
Because the trend of observed data looks more like a straight line than the red line.
Yes, yeah. So in overall, this red line is followed. As I said, it comes from much broader range in dynamic range in length and mass. So in this case, yeah, it follows more a line. And this also is the interesting is that it's shallower in this sense. And many of the massive objects actually seems to be growing more in mass than in length, resembling more the hub-like structures than fibers itself, as you would define them as filamentary structures.
And the other way around for the lower mass objects, because they are all above.
Yes.
Just one question. Juan raised a question, and also
Yes.
David. So the question from Juan is, can magnetic pressure be excluded as a source of additional pressure in this environment? If yes, why the feedback flavored as an explanation of additional pressure instead of a magnetic? We know that Juan has he loves magnetic.
That's an interesting. No, I just said feedback because it was the obvious one for OMC1 and Flame Nebula compared to the other regions. But I know that there are magnetic field measurements in those regions. We cannot exclude magnetic field at all. It's just that in many cases we cannot probe it. So it's not easily, let's say, it's not easily accounted for in this sense.
Okay, Juan, if you have any comment, please write in the chat and we will, if any, reply. Okay. Thumbs up. So also David has a question about the relation between the observed filament width and the instrumental angular resolution. I guess David wants to know if about what is the scale of your spatial resolution that you can have
Yes.
in spectral resolution.
It's close to the peak there.
Yes. I mean,
Okay, okay, wait a second. Probably you want to. I will try to my computer because Davide.
maybe
Mute yourself.
You hear me?
Yeah.
Ah, okay. I understood that I cannot speak. Can I speak? I don't hear you.
Davide, go home.
Okay. No, I want to say thanks for demonstrating, for showing that there is no universal filament width at 0.1 parsec. I was among the opponents of these results more than 10 years ago, because I think that filaments show a self-similar behavior at many scales. So probably with a better resolution, in some cases, a smaller width would have been found sooner or later. My question is, of course, there is a coupling between the spatial resolution of the observations and the observed filament width. I also expect that at a certain point, this self-similar behavior should interrupt. I would like to ask you, what is the scale you expect to, the minimum scale, the minimum width you expect to observe for filaments once, for example, other facilities at shorter resolution will be available?
Okay. So as you can see from these plots, there is a clustering towards the, let's say, 3 beam scale, which is 0.27. So what we, let's say, we thought about is that we are actually close to the resolution limit in this sense. So if we go even deeper, probably we would see narrower widths. How like deep we can go, I have no idea in this sense, because at some point we should be able to resolve the, let's say, final structure, the final width before the transition into like another kind of structure. We have some higher resolution data that I'm working on, which are 1.5 arc seconds. So maybe those will help us in this sense, but I don't know what is the limit. So for sure in Orion, the widths would probably be narrower. So we are not resolving them necessarily at the maximum resolution that they could have, but I don't know what will be the limit in this sense.
Okay, thank you. So there were more questions. Sorry, there was also Milena before.
Thank you for very interesting talk. Probably you already said that I missed it. I'd like if you can explain how you derive the mass in your data, because you probably said that, and then comment after that.
Yep. So we used the total column density maps to derive the mass. So we once.
Derive the function.
Yes, I mean the original observations are from Herschel. What we did is to use this calibration here to basically connect the integrated intensity of N2H plus to the total column density. So these this correlation was found to work in previous studies, and we applied it. In this sense, we can directly connect the integrated intensity to the total column density. Once we have the structure and we know all these components, all these different N2H plus spectra associated to it, we would calculate the mass directly from the.
Mass from the H2 column density map.
Yes, exactly. Yes.
No, because it was not clear to me if you use the same Herschel-based column data when you compare mass, or you derive the mass from directly from the spectra.
No, the observations are the same, but we use them as a calibration, because otherwise the resolution would be around 18.2 arc seconds. So to maintain the same spatial resolution in our observations, we use this calibration of the integrated intensity with the column density, and then we use the N2H plus, the H2 column density to calculate the mass. We could have used like a standard abundance for N2H plus, but it was more risky because it may change highly across the survey, because some regions could have similar to standard value, other regions that have, for example, higher temperatures and massive stars the abundance of N2H plus may change. So assuming a single value would be risky in this sense.
Thank you, Andrea. I have a curiosity. Can you go back to the plot with length and mass of the fibers? So you have a large span in mass for fibers more or less of the same length. Have you already started looking at if there is some morphological, some position inside your regions in which more massive fibers are preferentially located?
Yes. Yes, this was, we didn't say anything because it was a bit too speculative, but so the more massive ones are those connected directly to these bright objects. They are not only seen in Twitch Plus, but they are actually like connected to continuum sources, for example. One clear example is OMC2 Fear 4, OMC2 Fear 6, and the millimeter sources in OMC3. So these are objects that are really massive, like 20, 30 solar masses. And those fibers that we identify in N2H Plus are related one-to-one with these objects. So we think that this is why I said resemble more hubs than fibers, in a sense that there could be a transition, that the object is no longer filamentary, but it starts to become some massive and more roundish object.
So there is another, there is also Milena.
No, just to let you know that inside the Herschel-Gulbet survey, there are also more or less all the region has been, the analysis on the filamentary structure has been performed in much more region with respect to the one that you showed in your plots in comparison with them, and especially maybe there are some region also which at much lower typical column density that maybe can help you to prove also the smaller region, for example, the lupus and for example.
Okay.
Yes, the last plot you showed the comparison of your data with the Herschel one.
Yes.
And yes, so just to let you know that there are
Okay.
also other,
Because
more or less all the region that are have been observed in the project now have published filamentary
So-
structure analysis.
If I can jump in before we go into the next question, link to comment, I think I suggest you to look at the paper Benedettini et al. 2015.
Not
Oh.
only that.
That is a-
Okay,
Not only
Sorry.
that.
No, but there is other measurement for the filaments
Okay.
that are also smaller than 0.1%.
okay,
Not only that, I mean, now this is a.
This is my comment, a chair comment, okay?
okay.
Anyway, there was also a question
Yes.
by
It
Alessio.
was more a comment to go back to the previous Milena's question about how you calibrate the
Yes.
density from the N2H plus. If I'm not wrong, it comes from the work of Alvaro, in which he had a very many points on the low part of the column density, a few points in the high one, which you extrapolate the line, right?
Yes.
And I remember there was some discussion about how trustworthy can be at the high column density data. So I was wondering if your column density are within the range in which the fit is very well constrained by points, or you are already above that kind of fit. That I don't remember. It was more a comment out of that.
No, it's the same because the resolution is the same. So in the resolution and also the high end of the column density, which is OMC1 in both cases.
Okay.
So in this sense, it's fine. As you move to like even more massive regions or higher resolutions, and you can resolve actually the N2H plus emission, you may incur in problems because N2H plus 1 to 0 becomes optically thick, and then you have a flat profile. Yes.
Okay, thanks.
So any other question? I don't see any, so I will first before I will also have a comment basically because you mentioned about the relation between the width of your filament and the different you tested the different reason different parameters to check what are these systematic changes in the width. And the one that you showed us that's promising, and for me, if you put that in linear scale instead of logarithmic scale, will show better your decreasing trend. You mentioned that is with the central density, but have you tested also other quantities? For example, I was thinking about the amount of dense gas that you have, or the crowdness, other parameters on the x-axis instead only having the central density.
So we didn't test, with the, for example, the total mass, we didn't test with that. It could be an idea. I mean, other parameters, we thought that this one was the easiest, so the peak column density, because of the previous works. But yeah, I mean, we could try some other comparisons. We tried at some point to infer a volume density from the N2H plus emission, but it was a bit too speculative because, I mean, even if N2H plus has the hyperfine structure of the line, it was really, with one transition, it was really speculative to calculate the volume density. So we stick with that one.
I see. Okay, thank you. We can thank the speaker again.